Okay, good morning. This is, January 27th, 2025, ELEC 1013, Network Cabling class, Fanshawe College. Today we'll talk about, it's going to be the first part of coaxial cable, multiplexing, broadband, and baseband. We are also going to spend a great deal of time on something that's called impedance and characteristic impedance. Once in your life, you should have that lesson and just put it away on the shelf so you know what somebody's talking about when they're talking about this. And I'm talking about impedance and also something a little different. It's called characteristic impedance, all right? Which I haven't mentioned here. So it's a two-part lesson. So today you're going to get the first part of that. All right, now can I switch things? Yes, I can. All right, so coaxial cable, coaxial or sometimes it's called concentric, because here is one conductor right here. Okay, let me just get my laser pointer. Here is one conductor, and here is also another conductor that also acts as a shield, and they are those two conductors, which form a pair. They're separated by dielectric. It was a dielectric insulator. Well, dielectric is insulator, so insulator. There we go. And of course, plastic jacket or whatnot. Jacketing is subject to the need of the situation. So, excuse me. Sometimes you're going to have fire-rated jacketing. Sometimes fire-rated is not necessary. Sometimes you have to have UV, ultraviolet-rated jacket, so you can have that cable outside and not get damaged by the sun exposure, and so on. So whatever else goes here. Okay, so the thing is. The idea is that the one conductor is kind of like cladded, embraced, embedded, hugged by the other one. So this one here and that one here, they share the same center point. So they are called sometimes coaxial cable, or because they share the same, for the same reason, sometimes they're called concentric cable. So same thing. Now here is a picture of a coaxial cable. Here is the center conductor. Here's the dielectric that is separating the other conductor or ground reference, that also acts as a shield, preventing, the idea is to prevent interference from outside to get into the signal and interfere with the signal. And also it is, the idea is so any of the signal doesn't escape. How does that face the reality? The results are different. In many cases, I'll just tell you that. But the attempt is there, and it's, relatively successful. So again, two-conductor cylindrical transmission line, typically comprised of, center conductor insulated dielectric material and outer conductor shielding. Sometimes there's a double shield, sometimes there's extra shielding there. All right, the series of standard types of coaxial cable were specified for military uses in the form of RG or RG, and here's the number, RG whatever number, RG whatever number. The RG designation stands for radio guide. All right. This type of cable was mostly developed for the purpose of using it with a radar that was a newly developed thing just the beginning of World War II. And somehow the signal from the antenna of the radar had to be conveyed into the receiver and transmitter or transceiver, and that was in the form of a radio wave. So the radio wave you could send over the air, or the radio wave you could send over a cable. So this cable was, the purpose of this cable was to transmit radio waves. So RG stands for radio guide, for radio waves guide, so RG. And then the numbers that you're going to see, the numbers pretty much, you can safely say, do not mean anything. For example, the cable that mostly you're going to see if you have a cable internet in terms of like what type of internet provider do you have? Like how is it getting to your house? Is it fiber? Is it DSL? Oh, I have a cable. So that's the cable thing. It's RG6. That's what RG6 looks like. The RG6. What's 6? The 6 means nothing. It's just the engineers, after developing RG6 or a certain type of cable that serves certain purpose with certain specifications, they had to register that as something. And number 6 was available, so they just put number 6. So then we have RG6. Okay. And then RG6, for example, U, the U stands for UV rated. Okay. Now, a series of standard types of coaxial cable. They date from World War II and were listed in. There's a document, you can Google that and see how things were specified then. And there's a little thing. These designations are now obsolete because, well, they're from World War II. So, but coaxial cable is still being used today. For example, in order to provide the internet signal to the buildings. Not too long ago, actually, this was the major medium over which a cable TV was delivered. Now, we're going to look at 4 cables. The 4th one is not listed here, but I will tell you what it is. We're going to look at RG59, RG6, and RG11. Remember, the numbers do not mean anything. They're just a cataloging number. After the cable was developed, it had to be named something, so they named that number. Named that with the number. As far as the size comparison, they compare about sort of like that. This is the RG6 cable. Now, of course, this is not to scale because, well, you have a monitor, somebody else has a tablet, somebody else has a cell phone that you're watching this thing on, but the comparison between sizes, so the probably the most common thing that you could visually recall is the RG6 cable, because that's the size of the cable that the internet is getting into your house if you have a cable internet. Right, then RG59 is slightly thinner, right, in diameter, and then RG11 is wow, it's like wow, quite bigger in size. Okay. Now let's get some background here, because we're going to talk about something that is called a characteristic impedance. Okay. You need to know. Now, sometimes when you order a cable from a distributor or whatnot, when they ask you what impedance do you want, what impedance do you need, or something like that, they mean characteristic impedance. Sometimes they don't know that they mean characteristic impedance, but they actually do mean characteristic impedance. So let's, I'm going to spend some time explaining things to you. I need you to get the idea of what characteristic impedance is, but before we can get to that, let's review in somewhat detail of what actually impedance is. Now this here, it might be nothing new to you. It might be completely something new to you. I'm teaching the whole class. So after this, when it comes to this subject, hopefully we're going to have everyone on the same page as far as this topic is concerned. And by the way, this lesson will help you with learning the ideas with other, well, it will help you with other subjects for sure, right? So get a good coffee and let's start here. Now let's get some background information here. Let's take a look at the resistor, capacitor, and inductor, or a coil. All right. Now, resistor is a non-reactive component because its resistance value remains unchanged if the applied frequency increases or decreases. So if the frequency changes, the resistor will still have its own nominal resistance. If it's a 100 ohm resistor, whether you run DC through it, it will give you 100 ohms of resistance. If you run 100 hertz AC current through it, then it will still give you 100 hertz. If you run 1 kilohertz, 10,000 hertz, 20,000 hertz, it will still give you 100 ohms. It will not change. So it's non-reactive, which means it does not react to the changes of frequencies if their frequencies are changed that are applied to that component. Now, capacitor and coil. Capacitor is a reactive component because its resistance, and now I put that resistance in quotes here, and we'll get to that. Capacitor is a reactive component because its resistance value changes if applied frequency changes. Right? Now I can say the same thing about the coil. Coil also is a reactive component because its resistance value changes if applied frequency changes. Now, see when I had that thing in quotes? So let's keep going. Because the so-called resistance of the nonlinear component or non-reactive component, I should probably get rid of that nonlinear thing, is affected by the frequency changes. Because, let me rephrase that, because the resistance of the component changes when the frequency changes, we say that this component has a reactive resistance because the resistance value is a reaction to the different frequency. Depends on the frequency. So to simplify things, we call it reactive resistance, and it just so happened that we started calling that reactance. So reactance is a reactive resistance. Now, when it comes to capacitors and inductors or coils, the reactance that describes the reactance that is associated with a capacitor is called capacitive reactance, and it's designated as XC. For the inductors, it's an inductive reactance, and it's designated as XL. All right. The formula for that, for capacitor, is 1 over 2 pi frequency in hertz, and the capacitance of the capacitor in farads. Okay. And this here would be expressed in ohms, just like resistance is expressed in ohms. Now, for inductors, it's, well, almost the same thing. It's just you don't have that inversion, so it's going to be 2 pi, the frequency in hertz, and, excuse me, and the inductance in henries. Okay. So here is that. So now we get the idea of resistor, that is a non-reactive component, capacitor and coils are reactive, but well, they're kind of reactive in a different way. However, they're still reactive. Now let's see here. We keep going with the impedance. Get a sip of coffee here. Consider a non-reactive component as a resistor. All right, right here. So we just what we had at last on last page, and here we have AC source and AC source for capacitor and a coil. Right? What did they write here? Few years ago. Changes of the frequency does not affect. Okay, the capacitor, the pure DC. All right. So you can just see here, just looking at the formulas, the reactance or capacitive reactance, which is basically a resistance, depending on frequency. Let's see how how things are going to change with the capacitive reactance. If the frequency goes up, is the reactance, the capacitive reactance, going to go up or down? Look at this formula here, and let's say the frequency goes up. Then this thing here, the resistance of the reactive resistance or the capacitive reactance is going to go up or down when the frequency goes up. Can anybody take a shot at this? Quick answer. We got 33 people here. Somebody must be brave enough. I'll give you imaginary candy for being brave. It's pretty obvious here, but I'm just trying to see if you're paying attention or if you just, logged in and playing video games. No? All right. So I will leave that with you. Same thing here. If the frequency goes up in this formula when it comes to coil, when the frequency goes up, do you think that the inductive reactance is going to go up or down? Maybe somebody can answer that if somebody wakes up. All right. Here we have a circuit. I multi-sim that. You can do that as well. By the way, this is... oh, somebody said that. Okay, so we go up. Let's see here. Which one are you talking about? So, Clark, we get this here. If the frequency goes up here, is the reactance going to go up or down? This one down and the other one up. There we go. Finally, I thought you guys were sleeping. Good. You make me so proud because you're not sleeping. There you go. Excuse me. All right. So now I multi-simmed a circuit. By the way, this here, if you haven't discovered that yet, it's called a current probe. Because oscilloscope is not able to measure current, it's just able to measure voltages. But there's something that you can have that's called current probe, and it's one way of trying to display the waveform of current. In multisim, it's solved in that way here. So what do we have here? We have a power supply, and we have a switch. Through a switch, it goes through a 1 kilo ohm resistor. Then we go to a capacitor. And we close the circuit right here. So what is going to happen when we turn the switch on? All right. Here is the power supply waveform. It goes like that. I made a square wave because I wanted the sudden changes. I just wanted to have those sudden changes. Right? Now, here is the voltage across the capacitor, and here is the current across the capacitor. Now, how does the capacitor work? Let's say, let's make one big assumption that the capacitor is not charged. It's completely discharged. Those two plates that are close to each other, separated by dielectric, there's no charge. They are neutral with each other. So when we close the switch, the capacitor is going to start charging. And when the capacitor starts charging from being completely down to zero discharged, it is going to really basically drain the current because it's going to start charging. So in the beginning, it's going to look like a short here, like as just if there was a piece of wire. But after a while, when the capacitor gets charged, and it gets charged more, and it gets charged closer to its full capacity, then it's going to draw less and less current until when it completely charges, it's going to stop drawing the current. Okay? So that's what happens here. Okay, so this is the current. As soon as you close the switch, boom, here is the AC, here's the power applied. The current goes all the way, it just skyrockets to the maximum. And when the capacitor is charging, the current is going to go less and less and less, and it's going to stop flowing. Now, because it's acting as a dead short in the beginning, the voltage across the capacitor is going to be zero, because it's acting as a short, because, well, it conducts as much electricity as possible. So the voltage across the capacitor is going to be zero. But when the capacitor keeps charging and the current is going to get less, so then the voltage across the capacitor is going to show as, well, the maximum that it can be when it's fully charged. And the cycle repeats here. Okay, so that's the capacitor. So when you're looking at the capacitor, what goes first? What flows first? What appears first? Voltage or current when it comes to capacitor? By looking at this graph right here, we get current appearing on that first, and then we get voltage. So in capacitor, current leads the voltage. You just have to remember that for other subjects. Current is first in capacitor, followed by the voltage. So current leads voltage in capacitor. Here is a magnified version of that. Now, what else do I have? Other things that are associated with capacitors. Capacitors love change. The more often you change, the more the capacitor will work with you, and it will let you pass the current through it. If you stop changing and remain constant, the capacitor will eventually stop passing the current. On this graph, when the supply voltage changes, the current flows at its maximum. This means that it's the beginning of the... on this graph, when the supplied voltage changes, the current flows to its maximum. Okay? Change, boom, maximum current. This means that in the beginning of the change, the resistance is zero, Okay. So the voltage across the capacitor will be equal to 0. At the same time, as the time passes, and there is no change, the current will decrease until it stops. The capacitor resistance will go up. Means that the voltage across the capacitor will also go up. So in capacitor, the current flows first and the voltage builds up later. Current leads, voltage lags. Now, because this ELEC de-icement, ELEC de-icement, it's the acronym. See, ELEC, ICE, all right, man. You can hear is the E or voltage, inductor, current, capacitor, voltage, ELEC, icement. So you can remember it that way, but I would rather you get to understand what's happening so you don't have to remember acronyms. Here is a coil. Okay. Here is a coil. Instead of a capacitor, we get a coil. We get the opposite with the coil. Look at this. I kind of magnified the timing on this just to see things better in this case. The power supply changes all of a sudden from 0 to whatever it is, high. Look what's happening in the coil. Because coils, capacitors like change. Coils, the opposite, they hate change. They want to remain constant. So, if the coils do not like change, they will try not to conduct the current if there was no current going on in the first place. And if there is some sort of a sudden force applied to push the current through it, then the coil is going to react, trying to block the current if it's done too sudden. So what's happening here? Of course, this is a very sudden change from 0 to high here. So here is the current. You see, it doesn't start right away. And here's the voltage. Here's the opposite voltage. Boom! It just shuts up. It just shoots. The voltage shoots against the power supply to block the current. So in coil, the voltage gets first. You can see the voltage first, and then as the time passes, and you see there is no change. There's a change and there is no change. So the coil is going to say this: okay, I didn't like what you just did, but if you stay that way, then I'm going to cooperate. So I'm going to start, maybe I will start conducting the current and start letting it through. So then the current goes up. And of course, when the current goes up to the maximum, of course, then the voltage will go down because there will be no resistance. So the coils are the opposite of capacitors. Capacitors like change. Coils do not like change. Excuse me. Right. So when you apply frequencies, if you have a capacitor in the circuit, and you apply 100 hertz through the capacitor, you expose the capacitor 100 hertz, and which is in series with some sort of a circuit, then it's going to let you pass the current. But if you increase the frequency to, like, say, 1000 hertz, it's going to let you pass the current even more. It's going to resist even less. So the bigger the frequency, the less resistance capacitor is going to give you. Coils are just the opposite. When you increase the frequency, the coil will not like that and will just try to stop you from doing that, trying to send you the message, don't do that to me, I don't like change. So the bigger the frequency, the more resistance the coil is going to give you. The less frequency, the less resistance the coil is going to give you here. All right. So this is the visual, magnified visual of the coil thing. Let's just say here, inductors oppose change. The more drastic the change, the more inductor will resist. If the change stops, the inductor eventually will agree to the new situation and it will resist less. On this graph, when the supply voltage changes, there is no current flow, but the tension, which is voltage, is there from the start. This means that at the time of change, the resistance of the inductor is high, as opposed to the capacitor. So the voltage across the inductor is also high. As the time passes, and if there is no change, the current will begin to flow, the inductor's resistance disappears, which means that the voltage across the inductor, yes, that should be inductor, will also disappear. There's a mistake here, okay? This should be inductor. So in inductors, voltage appears first, and the current flows later. Voltage leads and the current lags. Just the opposite of, and you can just see here, you can just see those two graphs. In capacitor, current leads, it appears first. And inductor, voltage appears first. You can kind of stare at this thing for a little bit until things start emerging. There's another thing that I want to talk to you about. It's inductive reactance and capacitive reactance. When you put them together, at some point, if you get two components, one capacitor, one inductor, and they will have certain values. And when it comes to plotting the frequency response and as far as the reactance, well, it says impedance here, but we're talking about reactance and frequency. So here is inductive reactance in red, and here is capacitive reactance in blue. So if the frequency is really low, the inductor will conduct quite freely, and when you increase the frequency, it's going to start resisting, and it's going to have some sort of plot depending on its value. So inductor of 100 millihenries, just like Henry, the name, then it will look something like this in the logarithmic scale. So here's 10 hertz, 20 hertz, 30 hertz, 40 hertz, 50, 60. All right. Now, when it comes to getting certain size of a capacitor, let's say we're getting 100 microfarads, then of course when the frequency is low, then the capacitor is going to resist more. So the curve is going to look like this. For these two, 100 microfarads capacitor and 100 millihenries coil, at some point when you put those two graphs together, you're going to have some kind of a frequency that is going to have the same reactance for both of them. That's an interesting phenomenon when that happens, because in this case we call that resonant frequency. So for the capacitor of 100, like this value here, 100 microfarads and 100 millihenries coil, the resonant frequency is 50.4 hertz. Now, what do we have here? Over here on the top, we have the voltage across the capacitor. Here is 10 volts RMS, 1000 hertz, so 1 kilohertz signal going on, switch, resistor just to limit the current, and we have in series capacitor and a coil. All right. So the voltages across those two are going to look like this. Look what happens. Look, there's one interesting thing about those, because in capacitor the current leads and voltage lags, and in the coil voltage leads and current lags. Then we're going to have those voltages and the currents, but let's say voltages, we're going to have them out of phase 180 degrees. Okay, so they are just like mirror images. What goes with that? What is directly proportional to voltage? To voltage, directly proportional is resistance. The more resistance you have, the more voltage you're going. So if this resistor is part of a larger resistor network, if you change the resistance, keep changing that. If you increase that resistance, you're going to have, providing that the current flow is the same, then across the bigger resistance, you're going to have the voltage is going to increase. Of course, if you decrease the resistance down to zero, pretty much, then, well, you're going to have zero resistance and you're going to have zero voltage on that, right? So you can say that the reactances are also 180 degrees out of phase. Now we're getting somewhere with that, because reactance is the reactive resistance. Because the voltages are out of phase, 180 degrees, proportionally, naturally, the reactances, that means the reactances are also 180 degrees out of phase. What's going to happen when we have that resonant frequency? In capacitor, we're going to have a reactance pulling one way, and with the coil, we're going to also have a reactance pulling another way with the same value. They're going to cancel each other out. So if it's in series, and if it's at the resonant frequency, they will cancel each other, and it will be just like piece of wire. It's just like they don't exist. The whole circuit is going to look like power supply, switch, resistor, and the other end of the power supply. All right. When it comes to impedance, here, all loads are resistive, capacitive, and inductive. Everything will have a little bit of resistance because it's made out of physical thing. Everything will have a little bit of inductance, which is characteristic of a coil. And we'll have some capacitance because we are made out of physical things. It's just which quantity of the specific component that we designed and produced, which is the dominant part of it. So in capacitor, the dominant quantity is capacitance. The resistance and the inductance that is there are so small that can be completely ignored. Right? So All loads are resistive, capacitive, and inductive. The behavior of the load in the circuit depends on the type of signal or power applied, the proportions of its load characteristics. Many components are considered to be dominant in certain way, which is like just said, for example, blah blah blah, which is what I just said. Here is how we go with the impedance. Remember this thing here? All right, you might want to go back to it once you review the notes. In a circuit like this, we're going to have a certain amount of reactance and certain amount of reactance going the other way. So here is inductive reactance, and here is capacitive reactance. And then, of course, the resistance is always going to be at the angle, at the angle of 0. Okay? Impedance is the combination of resistance and reactance, or the total reactance. If we're not at the resonant frequency, so which is the frequency other than resonant, obviously, then one of the reactance is going to be greater. In this case here, the inductive reactance is greater than the capacitive reactance. So the total reactance is going to be this one here minus that. So it's going to be just that much shorter. That's going to give us the total reactance. If you draw a dotted line to that point here, and you draw the line like this, this is our impedance, and it will have an angle. So if the inductive reactance is dominant in the circuit, then we could say that this load that consists of many components, or maybe one, whatever, this load is inductive. Same thing here. See, the impedance does have an angle. Same thing here with the capacitive load. In this case, the capacitive reactance is way greater than the inductive reactance, so things are going to sway downwards here towards the capacitive reactance. So the total reactance is going to be that here, this area right here, from here to there, minus that, so it's going to be slightly shorter. Draw a dotted line, draw that here, and you're going to have impedance, but it's going to have a different angle. And one way you can do is you can do trigonometry, or you can do Pythagorean theorem to find out the magnitude and the angle of the impedance. Now, when it comes to cable, so we know now what impedance is. That was a whole, long lesson here. Now, we're getting to the punchline of this whole thing. Cables also have conductance, capacitance, and inductance. Conductance is the opposite of resistance. Capacitance, the opposite of capacitive reactance, and so on. So they have that, which means all cables will have impedance. Now, just bear with me here. I'm gonna fire something. I gotta fire up my board. Excuse me. We're almost done. If you have to go, you can go, but it's going to take about maybe 3 more minutes, and I'm going to wrap things up for today. Huh. 300 dpi. Yeah, that should do. All right, here's my board. If we're looking at a cable, coaxial cable, if we're looking at the coaxial cable, how come I can't write? I got it here. And I guess this thing doesn't want to cooperate with me. Pencil. And I don't know. It's probably gonna have to. All right, I'm gonna explain that thing to you. I'm gonna have to close that thing because something doesn't work. All right, what is capacitor? Capacitor is couple plates. There's one plate, and there's another plate, and there is a lead to it, and there's a lead to it, and that's that's how things are. The bigger the plates, the more capacitance. The closer together the plates, the more capacitance, and so on. But the bigger the plates, the bigger area of the plates, more capacitance, which means the reactance is going to be changed, which means the impedance will be also affected. So if we just drill a hole, you drilled a hole in this cable and we connected a line into the center core somewhere in the middle of that cable and brought it out, and the other line we connected to the other conductor, which is the shield or braiding, and also we could say that the capacitance of that cable will increase or decrease depending on the length of the cable. But we are not using cable that way. We're using cable this way here. We are injecting a wave into this cable, and we let the wave travel. Remember what I said, just notice what I said. We inject a wave, and we will let the wave travel on its own throughout the cable until it gets where it gets. Or maybe doesn't, because if the cable is too long. So, there is a concept in electronics that it's called maximum power transfer. In order to accomplish a maximum power transfer, we need to match the impedance of the output of whatever amplifier and the input of whatever the amplifier services. If you have those two impedances matched, then we get maximum power transfer, which means nothing heats up. The power is not dissipating as heat in the cable, or the power is not being dissipated as heat in the amplifier. So I'm going to say the third time. We inject the wave into the cable, and we let the wave travel on its own. So we are not interested in the whole impedance, as if we connected that by drilling the hole in the cable. We are only interested in how easy or how hard it is to inject a wave at this point. This is where the characteristic impedance comes in place. Just a little bit of a background. Permittivity is resistance to the electric field. Relative permittivity is the permittivity of material over permittivity of the vacuum. So here is the formula for the characteristic impedance, you see there's Z with the 0 here. That's like an indicator. And here's the formula. It's 138 over square root of the relative permittivity in the insulation between the two conductors, okay, times the log of this diameter over that diameter, blah, blah, blah. Here's the formula. Notice one thing. Nowhere in this formula is mentioned the length, the total length of the cable. Did you notice that? So the characteristic impedance of a cable does not depend on the length of the cable. With that formula, you can almost assume that the characteristic impedance of a cable is the impedance as if we drilled the hole in that and used it as a capacitor like that, if we had the first meter, just 1 meter of the cable. In some sources, they'll give you 1 foot. I'm not going to debate that. Because the wave is inserted in the cable and it travels on its own as it goes along. And then another wave is inserted. So why do we need to know the characteristic impedance? So we can interface it with this cable with the output of an amplifier, so we could match the output impedance of the amplifier for the purpose of maximum power transfer. So nothing heats up and you get good power transfer of the through the medium here. And that's all we need to know. So now you know the difference between the characteristic impedance, or between impedance and the characteristic impedance, and now you have some sort of idea of how this idea is being put to use. That's it for today's lesson, and I will see you next time. Some of you are going to see me in the lab session, and some of us will see each other in whichever comes first in the lecture. Okay? That's it for today. Thank you so much for your attention, and have a wonderful week.